In this video, we're going to build a demonstration cluster with AWS Parallel Computing Service. Now, it won't be the most sophisticated design, but it will show off the basics of working with PCS, and it'll get you ready to create your own HPC systems.
PCS is growing quickly, so we want you to know that if you see a message on your screen in YouTube here, there's a good chance that the video that you're watching right now has been replaced with a newer version. It might be a small change or a really big one, but either way, your life will be more pleasant if you watch the one that describes how PCS works today, not how it was in the past when we launched the service.
Now, if you want to follow along, this is the same cluster we built in Getting Started with AWS PCS in the PCS user guide. Let's get oriented to PCS by looking at the design for our cluster. In PCS, the Slurm controller and all the management logic for instances, monitoring, and so on is provided by a cluster resource. So you create and manage the cluster, but it runs on an account operated by AWS. PCS also has compute node groups. These are groups of instances with related configurations and rules for scaling. You can have one all-inclusive compute node group to handle everything, or you can have a lot of them, each with their own setup. That's totally up to you. Now in our cluster, we're going to have two node groups. One's called login. It's a static node group that always has one active instance. Its instance is in a public subnet so that it can have a public IP address, and it's configured to allow incoming access for SSH traffic, also from the public internet. The second node group is called Compute 1. Now, it can have up to 4 instances, but none of these will be launched until jobs are submitted to the scheduler. They're in a private subnet because there isn't need for users to connect directly to the instances. And also, it's not configured to even allow SSH from the public internet. Well, finally, we have PCS queues. These map to Slurm's partitions. You create a queue, and PCS configures the Slurm controller with the relevant partition. You can then assign the compute node groups to a queue so they can process work that gets submitted to that queue. Now, the queues don't really live anywhere, so I've shown them in a cluster in our diagram just for clarity. We'll have one named demo, and we'll connect it to the Compute 1 node group so that it has somewhere to send jobs to. So there's a couple of more details we need to talk about. First, notice that both node groups are connected to external file systems. We have an Amazon EFS file system that we use for home, and that makes it so your user directories are the same on every instance. And we have an Amazon FSx for Lustre file system mounted at /shared. That gives us the standard setup where you've got a high-performance directory to run jobs out of. Now in PCS, you currently have to specify network file system setups if you want them. So we're going to show you that. Now second, we haven't answered the question of where does the software come from. Obviously, you can install your own in the shared directories, but the instances still need to boot from something. And it usually makes sense to put common software like drivers and libraries right on the drive. So we'll cover this in another video, but PCS lets you bring your own AMI with your own custom software. And if you don't have one, we provide a sample AMI, and that's what we're going to use in our demonstration cluster. So that's it. Clusters, compute node groups, queues. File systems, sample AMIs. Hopefully this has given you a taste of what's possible with AWS PCS. Make sure to check out our other videos, blogs, and HPC recipes to learn how to tailor PCS to your own needs. So we're going to start by creating a virtual private cloud and subnets in multiple availability zones that can be used to support PCS and other HPC infrastructure. So to do that, rather than going and clicking around in the console, instead we're going to use a CloudFormation template provided by HPC recipes. You can either go to the repository and click on the HPC networking, the large-scale networking recipe, or you can download the template from a URL and upload it into the CloudFormation template or the CloudFormation console, which is what we're going to do right here. So we go to the console, we create stack with new resources, we upload a template. We leave all of these as their default values. This is going to create 3 private subnets and 3 public subnets. And now we wait until the status of this stack reads create complete. We won't be able to do anything until this is finished. So if you refresh the stack info a few times, after a couple of minutes, you'll notice that the status has reached create complete. That means that all of the resources in this CloudFormation stack are ready to be used with downstream dependencies like PCS clusters. So just quick orientation to CloudFormation. We won't go into great depth here, but quick orientation to CloudFormation. This is your stack overview page. You can find out all of the things that happened on your behalf while all of these resources were being created by looking at the events page. Two other important things are the resources. You can see what was created on your behalf. So you can see that. And then a lot of CloudFormation stacks also have outputs. And outputs are basically just text variables that the template author creates for you so that you can find out critical information about what went on in that stack. So in this case, the default private subnet is picked, the gateway ID, the list of all of the subnets that were created, the security group specific to this VPC, the ID of the VPC, all of these things are available as variables that you, in kind of pro mode, can use in other stacks. Finally, the parameters. These are the settings that you used when you actually created this stack. So you should recognize these. These are all things that we selected or entered into the fields in the forums interface before we hit go on the stack. All right, so that will be the case for. So this interface will be the case for all of the other CloudFormation stacks that we use in building out our demonstration cluster. After you've created your VPC, you need to actually navigate to the VPC console and find the ID for its default security group. Why do you need to do this? Well, when you create the Amazon EFS and Amazon FSx for Lustre file systems, they're going to be created by default with that default security group. You need to add that default security group to the login node and compute node groups in PCS. Otherwise, they won't be able to mount those file systems. So we're going to show you how to do this in the VPC console. Go to the VPC console, and you should be in the VPC dashboard. Under the VPC dashboard, select Filter by VPC. And find the VPC that you just created using CloudFormation. It will be called HPC Networking, Large Scale HPC. And select it. Then go down to your security groups. And this will show all the security groups associated with that VPC. But what you really need to look for is this default security group. It's called the default VPC security group. Select that ID. Write it down, put it in the notepad. It doesn't matter what you do with it, just remember it because you're going to need it later. So what's a cluster security group? Basically, this is one single security group that allows all the communications within the cluster. So what are we talking about here? The Slurm controller has to be able to communicate with the compute nodes and the login nodes. The login nodes need to be able to communicate with the Slurm controller. The compute nodes need to be able to communicate with the Slurm controller. And then the login nodes and the compute nodes also have to be able to talk to one another, depending on what kind of workloads you're running. The easiest thing to do is just to create one single security group that allows all of the members of the security group to talk to each other on all ports. That's what we're going to do for this example. However, a more sustainable approach, a more flexible approach, is to have at least 3 security groups. One for the cluster, and that basically controls ingress and egress to the head node and the controller. One security group at minimum for the compute nodes, and another security group for your login nodes or your clients. This is covered in depth in the PCS user guide. I highly recommend that you check this out as you start to build out your own production clusters. So the next thing we're going to do is we're going to create security groups. You have to have at least one security group before you create a cluster, and we need another security group to allow inbound SSH access. We're just going to create them together in one shot with one CloudFormation template so that we don't have to worry about it anymore. So to do this, it's going to look a lot like when we created the network just a second ago. We're going to open up the CloudFormation console. We're going to upload a template file. We're going to name the stack. In this case, we're going to call it Getting Started Security Group. Then under parameters, we're going to have two choices. One, we're going to pick a VPC ID. And in this case, we're going to pick the VPC that we just created. It'll be the VPC named HPC Networking. Then the other thing is we're going to fill in a client IP CIDR range. Now, what this is, and we don't need to get deeply into networking, but this is the range of IP addresses that will be allowed to connect to your login node from the public internet. So you can leave the default value, that will be 000/0. That lets any IP address connect, assuming they have the right they have the right SSH key, or you can restrict it to your own IP address or your own subnet range. We recommend that you do the latter, but for the sake of this demonstration, we're just going to proceed ahead with the wide open security group. We'll monitor the status of the CloudFormation stack, and when it reaches created complete, we can move on to start doing some really interesting work, like building our cluster. So now we're going to create a PCS cluster. Actually, this is just the head node, the scheduler, and some associated logic. It's not the compute node groups and queues. That part comes later. So this is just the cluster. That's just a convention that we use in the PCS service. Go to the PCS console, pop out the left nav bar and select clusters. Choose Create Cluster. Now let's name our cluster. I'm going to call mine Get Started. You have your choice of scheduler. Right now, PCS supports Slurm 2311. You can pick a controller size. Just choose small. Information about this is in the user guide. Basically, it's a factor of how many concurrent nodes and how many jobs can be concurrently managed by your PCS cluster. Pick a VPC, a subnet, and security groups. So here we're going to pick the VPC that we have created, the one named HPC Networking. We're going to pick one of our private subnets. I'm going to pick the private subnet A. And now we're going to pick a security group. We have a cluster Getting Started Security Group. We created this with CloudFormation a step or so ago. And that's all we have to add. You can actually have multiple security groups that you add to your cluster, but in this case, we only need the one. And we click Create. It takes a few minutes for your cluster to get created. Once that's happened, modifications like creating compute node groups and queues goes really fast, but the initial cluster setup takes a few minutes. So what we're going to do is we're going to let that cook for a little bit, and we're going to go off and create our two network file systems. What we're going to do now is we're going to create an Amazon EFS file system. So EFS is super elastic, relatively good performance. You wouldn't necessarily want to run HPC jobs on it or other or data intensive work on it, but it's fantastic for home directories or shared asset directories. So if you need to install user space software, or you need just common data sets, etc., EFS is really fantastic for that. So we're going to stand one of those up, and we're going to use that as the home file system on our cluster. To create a file system, go to the Amazon EFS console. Make sure it's in the same region where you are working with PCS. Sometimes when you switch consoles for the various services, it will default to another region, like US East or US West or something like that, depending on other things you've been doing in your AWS account. So I'm just going to double check. We're in Ohio. That's where our PCS cluster is being created, so we're in good shape there. Choose Create File System, and we're going to give it a name. Get Started EFS, and we're going to launch it in a specific private cloud, HPC Networking. We want all of these guys to be together in the same VPC. That makes it a lot easier for standing up a cluster. Okay, so EFS file systems get created blazingly fast. Basically, it's done now. Let's zoom in on it, grab the file system ID, and off screen here, I have a little notepad where I'm going to note that file system ID because we need it later. But now we're basically done creating our EFS file system. Okay, so creating the EFS was really simple. We click a button, and bang, we have an elastic file system. So now we're going to pull off the same trick, but we're going to do that with Lustre. So the FSX family of storage products at Amazon is really cool. I highly encourage you to check it out if you haven't. I absolutely, coming from an HPC background myself, I love the fact that I can go into a console and I can have a Lustre file system. And I can have a big file system, I can have a fast file system, and I don't have to run cables, and I don't have to wait weeks for the thing to burn in. In fact, there's a fantastically entertaining video in HPC Tech Shorts about building a terabyte per second Lustre system without pain or remorse. It's by the fantastic solutions architect, Randy Siemens. I highly encourage you to check that out. But we're going to create something a little bit more modest because all we're doing is kicking the tires with this cluster. Okay, so here we are at the Amazon FSX console. We're going to create a Lustre file system in just a handful of clicks. So we're going to choose Create File System. We are going to choose Amazon FSX for Lustre. We're going to name it. Get started FSX. If you're noticing a trend in my naming scheme, we can pick all sorts. There's a lot of bells and whistles and knobs that you can turn in configuring your Lustre file system. We're just going to leave everything here default except for the storage capacity, which we do have to say. We're just going to make it 1.2 terabytes. And we are going to turn on compression. I'm not going to talk in depth about this, but unlike in a physical data center, turning on compression often makes things faster. Here's the important part, down in networking and security. So we need to pick our VPC that we created. We're going to leave the security group, and we're going to pick the same subnet that we picked for private subnet named A. This prevents cross-availability zone network traffic, which nobody wants. It's a little bit slower, and you will incur charges across that. And the whole idea of an HPC system is high-performance networking and storage. So just make sure to pick the same subnet as where you deployed your cluster. All of this other stuff can be left default. We'll click Next. They give you a nice little interface for reviewing things, and then you can create your file system. No tears. So this will take 10 minutes or so to provision. Sorry, it's not absolutely instantaneous like EFS, but I think we can live with it. What we're going to do now is we're going to find the file system ID and the mount name. We need both of these values to configure the compute node groups so that they can mount this file system. So we're going to go here. We're going to copy the file system ID off to that off-screen notepad. And over here in the mount name, we're also going to copy that. Okay, so now we're done with FSX. We'll go on to the next part of the tutorial. By now, our cluster is done being provisioned. The FSX file system is probably provisioning away behind the scenes, but for now, since the cluster is done, we can go and we can create our compute node groups. So to create a compute node group, you need to do basically three things. First, you need at least one IAM instance profile. Remember, the IAM instance profile is what provides temporary credentials to every instance that launches in a node group. And you need at least to give each instance one entitlement, and that is the right to call home and tell the PCS API, hey, I'm up, I'm ready to join the cluster. And I'll show you what that means in just a second. Then you need to have a launch template, ideally one for each compute node group. We're going to create them together in a single CloudFormation template, just for the sake of simplicity. You can do them by hand. You can do whatever you want, but we're going to do it this way. And then you go into the PCS console and start defining your compute node groups, and you point them at the instance profile, you point them at the launch template, you point them at an AMI. So with that said, let's go ahead and create our IAM instance profile. Here we are at the IAM dashboard, and we're going to create an IAM instance profile. Now, this is just like creating a role. If you've done that before, it turns out when you create a role in the console like this, you automatically get an IAM instance profile created for that role as well. That's not the case if you use the SDK or CLI to create a role. At that point, you have to explicitly create a profile. So there's a little bit of behavioral difference between the console and the CLI and SDKs. So we're going to create this role. What we're going to do first is we're going to create a user-managed policy. This policy is actually what defines the entitlement that we want to give to our compute instances. So we're going to go to Policies, and we're going to choose Create Policy, and we're just going to pop in the JSON editor, and we're going to put in the following. Unless you think there's anything superhuman about me, I'm not typing this. I have this copied and pasted from an off-screen source. So all we're allowing here in this policy is we're allowing any instance where this policy is active can call register compute node group instance in the PCS service. And that's just an internal API that your instances call when they come up that basically lets PCS know that that instance wants to join the cluster. A little bit of information gets passed back that basically allows the instance to become a managed Slurm node. With that said, we'll just give it a nice little name, managed policy. Now we're going to create our IAM instance role. So we go create role. We select its use case is EC2 because this is for EC2 instances. We're going to search for our managed policy, and we're going to attach it. Okay, let's give it a name, AWS PCS Get Started Role. But we're going to add one more permission. So we have this phone home permission, but let's add the ability to be managed by Amazon SSM. SSM Managed Instance Core is what you're looking for. So now we've added another policy. We create that role, and if you look at the role, you'll also see that it's magically an instance profile, and it has an instance profile ARN as well. So now we're going to create two EC2 launch templates, one for the login nodes, one for the compute nodes. But we're going to do it with a single CloudFormation template, so that's cool. There are some inputs to this CloudFormation template that hopefully you wrote down in a notepad or a piece of paper. You need the default security group for the VPC that you created, HPC networking. You need the file system ID for your EFS file system. You need the file system ID for your FSX for Lustre file system. And you also need the mount name for your FSX for Lustre file system. You have all of these in hand, then let's go ahead and proceed with running the CloudFormation template, which will in turn create the EC2 launch templates. Here we are back at our old friend, the CloudFormation console. We're going to be creating a new stack, in this case, to create a pair of EC2 launch templates that can be used to configure our cluster. So we're going to create a new stack with new resources. We're going to upload a template. Again, this is hosted at HPC Recipes. The URL is also available in the user guide. We'll give it a name. Not going to get too creative. It's just going to be getting started, LT. Here are some parameters we have to pick. So the default VPC security group. This is, if you have multiple VPCs, each one of them will have a default security group. You have to pick the default security group for the HPC networking VPC that you created earlier. I wrote mine down, so I can just paste it in place here, and now I know I'll be happy. Oh, I don't have the cluster security group ID. What do? It turns out you can find it by name. So pick the one named Cluster Get Started Security Group, and we need our SSH security group. This one would be named Inbound SSH Getting Started Security Group. We need a key name. We'll pick one that I know I have access to, and now we need the file system IDs for our network file systems. So here's the one that we created earlier for EFS. Here's the one we created for FSX for Lustre. And remember, we also need the mount name. So we'll put that in as well. Kick this off. This will take literally just a couple of minutes. It'll create a pair of launch templates. The names will show up here in the outputs. In fact, voila, they are actually done. So compute getting started LT, login getting started, get started LT. You'll be able to see those in the PCS interface as you're configuring compute node groups. So in this step, what we're going to do is we're going to create a compute node group in PCS. And this specifically is our login node group. So in terms of configuration, this is going to be a single static instance. It's always up. It's going to be configured to allow inbound SSH access. It's going to have a public IP so that you can access it from anywhere on the internet. And this basically provides the blinking cursor, the prompt, the canonical interface to an HPC cluster. Just note, this is one way to do login nodes for PCS. The other way is you can bring your own instance. You can stand it up outside of PCS, and by following a relatively simple procedure, you can enroll it and attach it to the cluster and use that instance as your login node. So this is great for setting up workstations, workflow execution hosts, etc. It's a little complicated for a tutorial. I highly encourage you to check that section of the PCS user guide out, though. It's a really neat feature. Without further ado, let's go ahead and create our compute node group for login nodes. Here we are in the PCS console. Navigated to getting to clusters, our getting started cluster. You can see that its status is active, which means that we can start doing other configurations. Here's the default configuration, VPC subnet security groups. Where we want to go is we want to navigate to compute node groups. And we want to create a compute node group. We'll name it login. And we're going to select the login get started launch template. Then we're going to select the AWS PCS get started instance role. We'll pick some subnets. In this case, we're going to pick the public subnet A. The public subnet, just as a reminder, this is so that the instance will have a public IP address. We'll pick a relatively modest instance, a C6i 2x large. You can use any x86 instance here. We're just being frugal here. And we set our minimum and maximum instance count to 1. So we want one instance to come up and stay up all the time. Then we need to select an AMI. So when you click this drop down, all the AMIs that you have access to in your account will show up here. Easiest thing to do is search for the sample AMI by name. The pattern for this is AWS PCS sample AMI, Amazon Linux 2, AMZN2. Your architecture, x86-64, Slurm 2311. If by chance you see multiples, pick the one that is newest. That's a good practice. So 712, I'm doing this before the product launch. So that's the most recently built one. You can choose on demand or spot. Obviously, for a persistent set of instances, you want on demand. You don't want them to get reclaimed. And you can, of course, do a little bit of Slurm configuration, but we're not going to do that here. So here we just click create, and we will wait for the login node group to be created. That will then kick off provisioning of an instance, but we don't actually have to wait. we can go ahead and start creating the compute node group while this compute node group is in process of coming up and provisioning its instance. Here we're back at the main page for the Get Started cluster. We're going to create a compute node group. So this is for running jobs. So we'll give it a name, compute 1. There might be other compute node groups later. We want the compute get started launch template, not the login get started template. We want the getting started role. So in this case, both node groups have the same role. That doesn't always have to be the case. If you want specific permissions on your login and your compute nodes, you can indeed make it different. This is just for simplicity. So subnets. These are compute instances. They don't need to be on the public internet, so let's make them private. We'll put them in private subnet A, and we'll pick some instance types. Again, I'm going to be frugal and just do a C6i, make them a little bit larger, make them 8 cores instead of 2 like we did. And then our scaling configuration. This is really a key difference between this and the login nodes. Here, we want our scaling, we want this node group to have no instances when there are no jobs, and up to 4 instances when there are jobs running or in the queue. Then we need to pick our AMI. Again, we'll pick this most recent one. And again, just as an aside, in this case, in this cluster, the login nodes and the compute nodes have the same AMI. If, for instance, you wanted that to be different, you could build 2 AMIs, one for your login nodes, one for your compute nodes, and they can be different. They simply have to be operationally compatible within the cluster. So like theoretically, same general operating system, same set of users, etc. But otherwise, PCS is pretty flexible. Purchase option. If we wanted to, we could make these spot instances. I don't necessarily want to do that, but you could. And we kick off create. And if we go back to the getting started cluster, look at compute node groups, we can see that the compute node group is in the process of being created. Login is done and active. While we're waiting for the compute node group, compute 1, to come up, let's talk about queues real quick. So we need to have at least one queue so that we can submit jobs to it. But queues and compute node groups in PCS are really flexible. So you can have a queue that speaks to multiple compute node groups. If you don't provide any explicit waiting or ordering, jobs will just get assigned lexically based on the compute node names. You can also set waits. You can also do things like you can combine, you can have a queue that has multiple compute node groups that combine instance types. You can have a queue where the compute node groups are even different architectures, x86 and ARM. You can also have multiple queues talking to multiple compute node groups. Almost any mixture of queue and compute node group, like communications patterns or resource utilization patterns that you can think of, you can actually implement in PCS. It's very flexible, basically just like Slurm. Let's create a queue. So we want to add the compute 1 node group into a queue. Notice it's in the active status. If it's in the creating or updating status, you can't modify its association with a queue in PCS. So let's create a queue. We'll call it demo. And we can select the compute node groups that we want to associate with that queue. You can change this later. You can associate and dissociate compute node groups from queues just as long as they're in the active state. In this case, we're just creating one and attaching a compute node group to it. Okay, and there we go. You'll see the queue is in the creating status. It takes a brief period while the scheduler configuration is propagated to the cluster, and then we would be able to use it. So now it's time to connect to our cluster. So the way that you do this is through the EC2 console. Basically, you find the instance that PCS has launched for you. Now, if you've got a lot of instances, this could get complicated. So what PCS does is it tags every instance that it launches with 2 system tags. 1, the cluster ID, 2, the compute node group ID. And if you search for either the cluster ID or the compute node group ID, you can find the instances belonging to that cluster or that compute node group in the EC2 console. So that's what we're going to do. And when we're in there, because we've configured this instance to be accessible using AWS Systems Manager, Session Manager, we'll be able to connect to it right from the web. To connect to your cluster, go to the compute node groups in your cluster detail page and find the ID for your login node group. Select that ID, go to the EC2 console, go to instances, and search for that tag. So this will be AWS PCS compute node group ID equals blah, whatever it was. So here's our instance. You can see that it's running. It's been up for a little while. If we click on the instance ID, we can see all sorts of additional details about it. You can even see the IAM instance role. You can see the VPC and subnet that it's in, et cetera, et cetera. But what we really want to do is we want to connect to it. So if we have that SSH key handy, we could connect to it through its public IP address. But what I'm going to do is I'm going to connect using Session Manager. This will let me connect right in the web, right in a web browser. So here we go. I'm going to become the default user. And here we are. Somewhat anticlimactic. It's a login prompt on a virtual cluster. However, we can start to get some interesting information here. Is this really a Slurm cluster? Let's run some commands. We can run sinfo. All right, there's a partition, which is the Slurm name, the Slurm mapping for a queue, named demo. The partition is up. It doesn't have a time limit. It supports up to 4 nodes, and there are our compute 1 nodes sitting idle. They don't actually exist because they're just kind of mapped out in the scheduler. Obviously, we can look for jobs. What else can we do? So remember, we mounted home and shared file systems. So let's look and see what file system mounts we have on this system. So as we can see, /home appears to be an 8 exabyte file system. That is a very large file system. So basically all user accounts on this entire cluster on every single node are all on this EFS file system with nearly infinite capacity. That's pretty cool. We also have a 1.2 terabyte Lustre file system at /shared. So that's also pretty handy. With that said, now we can go ahead and proceed to run some test jobs, and we can actually kick the tires and prove the fact that this is a working Slurm cluster. Let's run an example job. Super simple, single node. Change to the shared directory, and we'll write out a sample job script. And we will submit this using sbatch to the demo queue. Boom. We run qstat, we can see the job thinks it's running. If we run sinfo, we can see that one of the nodes, compute 1.1, is in the mixed state. That means it's on the process of coming up. If we went and looked in the EC2 console, we would see an instance launching, getting ready to join the cluster, run the workload, and then after a period of time, spin itself down so that it's not accruing charges anymore. So we'll wait for a couple of minutes, and then we'll check on the output from this job, which we'll just write to a little output file. Okay, so it's been a minute. The node has come up. The job is done running. Let's inspect the outputs. More single one out. Here we go. Very complex stuff. This is a job. It ran on compute 1.1. It was submitted from this login node, and the job is complete. So we ran a really simple job. Now let's do a multi-node job that runs across multiple instances and uses the MPI communications library. And just to make it a little bit more interesting, we're going to compile the We're going to compile the software. It'll be on the home directory, but we'll swap into the shared directory, the high performance directory, to actually run the job. And this will demonstrate a pretty common usage pattern in HPC. So let's change to our home directory, write out some MPI C source code. Then we're going to load the OpenMPI module. And we're going to compile this code using MPI-CC, the MPI compiler. Okay. We can prove that that compiled. There's hello in our home directory. Now we need to write a little job submission script. So key thing, we're going to use srun to run home hello. We're going to ask for 4 nodes, 1 task per node, and it's going to be exclusive execution. So 1 task on each node. That's what this means. So let's cd to the shared home directory. And let's submit our job. And then we'll use SQ to monitor the job until it's done. So you can see the nodes are configuring. They're all on their way up. It'll take a couple of minutes for them to launch. They'll run the job. They'll write out outputs. Each task will write an independent piece of output, and then it will be done. So it's been a couple of minutes. Let's check to see if our job is done. Looks like, okay, the job's no longer in the queue. Nodes are idle. So now let's look at our outputs. Okay, so there are outputs from the multi-job. So are there any errors? Okay, no errors, that's good. And look at the output. Hey, 1 line for each task. Hello world from processors running on 4 different IPs. That maps to 4 individual nodes, just like we asked. So we have now successfully run an MPI job on Slurm. Now that the demo is complete, there's one more thing we have to do, and that is delete all of the AWS resources that were created in the course of doing the demo. Some resources won't necessarily incur a charge, but some will. We're not going to go through this step by step. This is documented very well in the Getting Started with AWS PCS section of the user guide, and I recommend that you go there. But basically what you need to do is tear things down in reverse order. So tear down the queue, tear down the compute node groups, tear down the cluster. Then go tear down the instance profile, the launch templates. Then you can get rid of the file systems. Then you can get rid of the security groups. And then finally, you can get rid of the VPC that we created for this demonstration.